In August 2025, astronomers at the Keck Observatory in Hawaii pointed their instruments toward a distant object crossing our solar system and saw something that shouldn't exist. A comet, racing past the Sun, had grown a tail pointing directly toward it. Not away from it, like every comet we've ever studied, toward it. This suggests complexities in how solar forces interact with cometary material. This wasn't a trick of perspective or an optical illusion. Spectroscopic analysis confirmed it. Gas was streaming from this object in the wrong direction, challenging existing cometary models of behaviour. You might think that sounds impossible. You'd be right to think that, because under normal circumstances it is impossible. But here's what makes this story even stranger. This wasn't humanity's first encounter with an interstellar visitor. Back in 2017, we discovered ʻOumuamua, the first confirmed object from beyond our solar system, and it rewrote the textbooks. It accelerated away from the Sun without visible outgassing. It tumbled through space in ways we'd never seen. It sparked debates that reached from NASA briefing rooms to social media threads about whether we are looking at alien technology. Eventually, scientists figured it out. Hydrogen outgassing, natural processes, mystery solved, case closed. We thought we understood the playbook now. We thought interstellar visitors would fall into predictable categories. Rocky wanderers like ʻOumuamua, icy comets like Tui Borisov, which behaved exactly as expected. Simple, explainable, familiar. And then 3I Atlas arrived. This object didn't just break the rules ʻOumuamua established, it shattered them, stomped on the pieces, and left scientists scrambling to explain behaviour that makes ʻOumuamua look downright ordinary by comparison. Where ʻOumuamua was quiet and mysterious in its silence, 3I Atlas is screaming with activity we can't fully explain. Where ʻOumuamua sparked debate because it didn't act like a comet, 3I Atlas is baffling researchers because it acts like a comet in ways no comet should. Stay with me. In the next several minutes, we're going to investigate why 3I Atlas might be the strangest interstellar visitor we've encountered, compare it directly to ʻOumuamua's famous anomalies, because what we're dealing with here isn't just another space rock. It's a challenge to everything we thought we'd learned from the first interstellar visitor. And the more data that comes in, the more questions scientists are asking. If you're watching this because something about this object doesn't add up, because you heard whispers about anti-solar tails and colour changes and chemical signatures that make no sense, you're not alone. Hit that like button and drop a comment telling me what brought you here, because this mystery is unfolding in real time and we're all trying to figure out what we're really looking at. The question isn't whether 3I Atlas is strange. The question is whether it's stranger than ʻOumuamua, and if so, what that tells us about the universe beyond our solar neighbourhood. Let's find out together, and let me show you why this visitor might be rewriting the rules one more time. Before we can understand why 3I Atlas is so unsettling, we need to go back to where this all started. October 2017, the Pan-STARRS telescope in Hawaii detected a faint point of light moving through our solar system at incredible speed. At first, astronomers thought it was just another asteroid or comet, but when they calculated its trajectory, they realized something extraordinary. This object wasn't orbiting the Sun, it was passing through our solar system on a hyperbolic path, meaning it came from somewhere else entirely. Interstellar space, another star system. For the first time in recorded history, humanity had confirmed a visitor from beyond. They named it ʻOumuamua, a Hawaiian word meaning scout or messenger, and from the moment scientists got a good look at it, nothing made sense. First, there was its shape. Based on how its brightness fluctuated as it tumbled through space, researchers determined ʻOumuamua was extremely elongated. Think of a cigar, or perhaps a pancake, spinning end over end. The length-to-width ratio was unlike anything we'd seen in our own solar system. Asteroids and comets are typically more rounded, shaped by billions of years of collisions and gravitational interactions. But ʻOumuamua looked like it had been stretched, as if formed under conditions we couldn't quite comprehend. Then there was its motion. As ʻOumuamua swung around the Sun and began its journey back into deep space, astronomers noticed something odd. It was accelerating. Not much, but measurably. It was speeding up as it moved away from the Sun, and this acceleration couldn't be explained by the Sun's gravity alone. In fact, it was accelerating in the opposite direction you'd expect if gravity were the only force at play. This is where things got interesting. When comets approach the Sun, they heat up. Ice beneath their surfaces turns directly into gas, a process called sublimation. This outgassing creates pressure, like a natural rocket engine, that can push the comet slightly off course. It's a well-understood phenomenon. Every active comet we've studied shows this behaviour, but here's the problem. ʻOumuamua showed no visible signs of outgassing. No tail, no coma, the fuzzy cloud of gas and dust that surrounds active comets, no detectable emissions in any wavelength astronomers checked. So you had an object accelerating like a comet but looking like an asteroid. An object from interstellar space behaving in ways that didn't fit either category we had for small solar system bodies. Naturally, this sparked debate. Intense, fascinating, sometimes heated debate. Some researchers proposed that ʻOumuamua might be a new class of object altogether. Perhaps it was a chunk of solid hydrogen ice, which would sublimate without leaving visible traces. Perhaps it was a fragment of a planet torn apart by tidal forces near another star. And yes, some scientists, including respected astronomers from Harvard, suggested it might be artificial, a light sail, a probe, technology from another civilization. You can imagine how that went over. Social media lit up. Suddenly, everyone had an opinion about whether we'd just witnessed humanity's first brush with alien technology. The speculation reached fever pitch, with documentaries and articles debating whether ʻOumuamua was a natural object or something designed and built. But here's what happened next, and this is crucial for understanding the 3i Atlas situation. Scientists kept studying the data. They kept running models, and eventually a team of researchers proposed an explanation that fit the observations without requiring anything exotic. Hydrogen outgassing. They suggested that ʻOumuamua could be releasing molecular hydrogen, which is invisible to most detection methods. This hydrogen could have formed through a process involving water ice being broken down by cosmic rays during the object's long journey through interstellar space. The hydrogen, trapped in the ice, would be released as the object heated up near the sun, creating just enough thrust to cause the observed acceleration. The beauty of this explanation is that it's entirely natural. It doesn't require new physics. It doesn't require alien engineers. It requires only processes we know happen in space, applied to an environment, deep interstellar space, where objects spend millions of years exposed to radiation in ways solar system objects don't experience. Most of the scientific community accepted this explanation, not because it was the most exciting option, but because it was the most consistent with known physics and the available data. ʻOumuamua went from being a potential alien spacecraft to being an exotic but natural interstellar comet with an unusual composition. Mystery solved, or at least explained well enough that scientists could move on. This resolution taught us something important. It taught us that when we encounter something from interstellar space, we should expect it to be different from what we're used to. These objects formed around other stars in protoplanetary disks with different chemical compositions. They were ejected through processes that might favour certain shapes or structures. They travelled through the galaxy for millions or billions of years, exposed to radiation and conditions unlike anything in our relatively sheltered solar system. Of course they're going to look strange. Of course they're going to challenge our models. ʻOumuamua set a new standard. It established that interstellar visitors could be weird, but ultimately explainable. It gave us a framework, a checklist, almost. Look for unusual acceleration. Check for outgassing, even if it's not immediately visible. Consider formation environments around other stars. Don't jump to extraordinary conclusions without exhausting natural explanations first. We thought we had the playbook figured out. We thought the next interstellar visitor would fit somewhere in this expanded understanding. Maybe it would be another quiet hydrogen outgassing object like ʻOumuamua. Maybe it would be an active comet like 2I Borisov, which arrived in 2019 and behaved exactly as a normal solar system comet would, with a visible coma and tail and outgassing that matched predictions perfectly. Either way, we had categories now. We had experience. That confidence wouldn't last long, because the next visitor was about to arrive, and it wasn't interested in following any framework we'd established. When 3i Atlas was first detected in 2025, there was excitement certainly. Another interstellar visitor, another chance to study an object from beyond our solar system. But there was also an expectation, a sense that we knew what to look for now. We'd seen the quiet mystery of ʻOumuamua. We'd seen the well-behaved normalcy of 2I Borisov. This third visitor would probably fall somewhere on that spectrum. Maybe it would be unusual in small ways, but we'd be able to categorize it quickly. That expectation lasted approximately as long as it took to point serious instruments at it. From the very beginning, 3i Atlas was different. Where ʻOumuamua appeared inert, showing no obvious cometary activity, until scientists worked backward from its acceleration, 3i Atlas was immediately and obviously active. It had a visible coma. It had brightness fluctuations consistent with outgassing. It looked, for all intents and purposes, like a comet, and that should have been reassuring. Comets, we understand. Comets are predictable. Comets follow rules. Except 3i Atlas wasn't following any of them. Let's talk about its trajectory, because this is where you start to appreciate just how far this object has travelled and how different its journey has been from anything in our solar system. 3i Atlas is moving on a hyperbolic orbit with an eccentricity around 6.1. If you're not familiar with orbital mechanics, let me put that in perspective. An eccentricity of 0 is a perfect circle. An eccentricity of 1 is a parabola, the boundary between a closed orbit and an escape trajectory. Anything above 1 is hyperbolic, meaning the object is going fast enough to escape the sun's gravity and will never return. An eccentricity of 6.1 means this object is absolutely screaming through our solar system. It's not lingering, it's not captured. It came from interstellar space, it's making one close pass by the sun, and then it's gone forever. But here's what makes it even more extreme. The orbital inclination is near 175 degrees. That means it's travelling almost perpendicular to the plane where the planets orbit, coming in from above or below the solar system's disk. It's not just fast, it's coming from an entirely different angle than almost anything we're used to tracking. In October 2025, 3i Atlas reached perihelion, its closest point to the Sun. This is when comets typically become most active, when solar heating is at its maximum and outgassing reaches peak intensity. Scientists around the world pointed every available telescope at it, eager to capture data during this critical window, and what they saw defied every prediction they'd made. The brightness was wrong. Comets have predictable brightness curves as they approach and leave the Sun. You can model how much light they reflect and how much their coma contributes to their overall brightness. 3i Atlas was brighter than it should have been at certain times and dimmer at others, fluctuating in ways that didn't match standard cometry models. It was as if the object was turning on and off, or perhaps changing what it was showing us. The activity level was extreme. Most comets release water vapour and dust in relatively predictable ratios. They brighten gradually as they approach the Sun, peak near perihelion, and then fade as they move away. 3i Atlas showed bursts of activity that seemed disconnected from its distance to the Sun. It would flare suddenly, releasing massive amounts of gas, and then quiet down again. It was behaving more like a variable star than a comet, pulsing with energy in patterns scientists couldn't immediately explain. And then there was the colour. Early observations noted that 3i Atlas had an unusual surface reflectance. Comets typically appear reddish because their surfaces are covered in organic compounds that have been altered by radiation over millions of years. Asteroids can range from grey to red depending on their composition. 3i Atlas didn't quite fit either category. Its colour changed depending on when you looked at it, shifting in ways that suggested its surface was being actively modified, or that different materials were being exposed as it outgassed. But all of this, strange as it was, could potentially be explained. Maybe it was a comet from an unusual formation environment. Maybe it had a particularly volatile Earth composition that caused the irregular activity. Maybe its surface was heterogeneous, with patches of different materials that rotated in and out of sunlight. Scientists were puzzled, yes, but not alarmed. Comets are diverse. Interstellar comets even more so. You expect some weirdness. And then the really impossible observations started coming in. The things that couldn't be hand-waved away with, well, interstellar objects are different. The things that made researchers stop and look at each other across conference rooms and say, wait, run that analysis again because that can't be right. Because 3i Atlas wasn't just acting like an unusual comet. It was doing things comets aren't supposed to be able to do, and the more data that came in, the clearer it became that this object was playing by an entirely different set of rules. Let me explain something fundamental about comets that every astronomer learns early in their training. When a comet approaches the Sun, it heats up. Ice on and beneath its surface sublimates, turning directly from solid to gas. This gas carries dust particles with it, creating the characteristic fuzzy coma around the comet's nucleus. But here's the key part. The Sun doesn't just heat the comet, it also pushes on it. Solar radiation, photons streaming out from the Sun, exerts pressure on the gas and dust surrounding a comet. It's not much pressure, but it's enough to push lightweight particles away from the sun like wind-blowing leaves down a street. At the same time, the solar wind, a stream of charged particles constantly flowing from the sun, also pushes on the ionized gas in the comet's coma. The result is that comets always develop tails that point away from the sun. Not behind them in their orbit necessarily, but away from the sun itself. The tail can curve depending on the particles' velocities and the comet's motion, but the fundamental direction is set in stone by physics. Away from the source of pressure, away from the sun. This isn't a guideline, it's not a tendency. It's a law based on radiation pressure and the behaviour of charged particles in the solar wind. Every comet we've ever observed, from ancient records to modern telescopes, follows this rule. Thousands of comets, centuries of observations, not one exception. Until August 2025, when astronomers at the Keck Observatory confirmed that 3I Atlas had developed a tail pointing toward the sun. Let me be clear about what we're talking about here, because there's a phenomenon called an antitail that people sometimes confuse with what 3I Atlas is doing. Antitails are optical illusions. They occur when Earth passes through the orbital plane of a comet, and we see the dust tail edging, creating the appearance of a spike pointing toward the sun. It's purely a matter of geometry, a trick of perspective. The dust isn't actually moving sunward, we're just viewing it from an angle that makes it look that way. Astronomers are very familiar with antitails. They're well understood and entirely explainable. What 3I Atlas is doing is not an antitail. Spectroscopic analysis confirmed that gas was actually being emitted from the object in the direction of the sun, not just appearing to point that way because of our viewing angle, actually moving sunward. The Keck Observatory detected emission lines corresponding to various gases, including cyanide compounds and metal atoms, in material that was streaming from 3I Atlas back toward the sun. This wasn't an illusion. This was real matter travelling in a direction it shouldn't be able to travel. Think about what this means. This behaviour is contrary to typical expectations based on solar radiation dynamics. Imagine releasing a helium balloon in a windstorm and watching it move into the wind instead of away from it. That's the scale of impossibility we're talking about. The forces pushing cometary material away from the sun are powerful and unidirectional. There's no known mechanism by which ordinary outgassing could overcome that pressure and send material sunward, unless the outgassing itself is profoundly asymmetric. This is where scientists started developing hypotheses, trying to explain the unexplainable within the framework of natural processes. If 3I Atlas has jets of gas erupting from specific locations on its surface, and if those jets are oriented in very particular directions, it's theoretically possible that the material could be moving in unexpected directions relative to the sun. Picture a rotating sprinkler, but instead of even streams, some of the nozzles are pointed in different directions and firing at different intensities. Now put that sprinkler on an object tumbling through space, being heated unevenly by the sun, and you might get extremely complex outgassing patterns. But even that explanation struggles to account for what was observed. The anti-solar emissions weren't brief or localized. They persisted over multiple observation periods. They involved substantial amounts of material, and they included not just gas but also signatures of metals and other compounds that should have been swept away by solar radiation pressure the moment they were released. Then there's the nickel. Oh, the nickel. We need to talk about the nickel, because this is where the chemical composition of 3I Atlas starts to raise even more questions. Spectroscopic observations detected strong emission lines from nickel atoms in the anti-solar tail region. Nickel is a metal. It's heavier than most of the gases typically associated with comets, and it was present in quantities that didn't make sense, not just in the anti-solar region, but in the object's emissions overall. Here's what makes that strange. In our solar system, when comets release metals, those metals typically come from dust grains that are being heated and vaporized near the nucleus. The presence of metals tells you something about the comet's composition, about what minerals and ices were present when it formed. But the ratio of different metals, and the abundance of those metals relative to other elements, follows patterns based on cosmic chemistry. The building blocks of planetary systems have certain proportions of elements based on how stars forge those elements through nuclear fusion. 3I Atlas had nickel in abundance, but detections of other metals you'd expect to see alongside nickel, like iron, were either weak or absent. It's as if someone had chemically sorted the object, concentrating certain elements and depleting others in ways that don't happen naturally in protoplanetary disks. Or at least, not in ways we understand. Now, I want to be very careful here, because this is where speculation can run wild if you're not disciplined about it. The presence of unusual metal ratios doesn't mean the object is artificial. It doesn't mean it's a spacecraft or a probe. What it means is that 3I Atlas likely formed in a very different chemical environment than solar system comets, under conditions that favoured the incorporation of certain elements over others. Maybe it came from a protoplanetary disk around a star with an unusual metallicity. Maybe it formed in the debris field of a stellar collision or a supernova remnant. There are natural explanations for strange compositions. But here's the thing that keeps scientists up at night. It's not just that the composition is strange. It's that the composition is strange in combination with the impossible tail. It's strange in combination with the extreme activity fluctuations. It's strange in combination with all the other anomalies we'll discuss in a moment. Any one of these things in isolation would be fascinating but explainable, a curiosity, a footnote in a research paper. It's the accumulation that creates the sense that something is deeply off. It's the way each new piece of data doesn't resolve the mystery, but instead adds another layer of weirdness. And that's exactly what happened as observations continued, because the anti-solar tail and the nickel emissions were just the beginning of what 3I Atlas had to show us. If you were writing a detective story, you'd say that every object in space has a fingerprint, a unique chemical signature that tells you where it came from, what it's made of, and what kind of environment shaped it over millions of years. Spectroscopy is how we read those fingerprints. When light from an object passes through a prism or diffraction grating, it splits into its component wavelengths, and certain wavelengths are either absorbed or emitted by specific atoms and molecules. Each element and compound has its own unique pattern of lines, as distinctive as a barcode. When scientists turned spectroscopic instruments toward 3I Atlas, they expected to see a fingerprint that looked more or less familiar, maybe shifted a bit because of different isotope ratios or unusual abundances, but still recognizable as a comet. Comets are primarily water ice mixed with frozen carbon dioxide, carbon monoxide, methane, ammonia, and various organic compounds. When they outgaze, you see emission lines from water vapor, cyanide radicals, hydroxyl groups, and dust that reflects sunlight. It's a messy spectrum, but it follows a pattern. 3I Atlas's spectrum wasn't following the pattern. Let's start with the water, because water is the most abundant volatile in comets. It dominates everything. When a comet gets close to the Sun, water sublimation accounts for the vast majority of the gas and most of the activity you observe. The water production rate tells you how active the comet is, how much material it's losing, and roughly how large the nucleus might be. For a typical comet at the distance 3. I Atlas was from the Sun. You'd expect a certain range of water production. 3I Atlas was ejecting water at rates that made it look like someone had aimed a fire hose at the Sun and turned it on full blast. The sheer volume of water vapor pouring off this object was extreme, especially given its estimated size. It was losing mass at a pace that suggested either the nucleus was far more volatile-ric than normal comets, or something about its internal structure was allowing heat to penetrate much deeper than usual, triggering outgassing from subsurface layers all at once. But here's the contradiction that baffled researchers. Despite this massive water production, the dust production was surprisingly low. Comets typically release gas and dust together. The gas carries the dust. The ratio of dust to gas tells you about the comet's composition and structure. A dust-rich comet appears redder and develops a thick, bright coma. A gas-rich comet is bluer and has a more diffuse coma. But extreme gas production with minimal dust, that's unusual. It suggests the object is either made of very pure ice with little rocky material mixed in, or the dust is somehow being retained while gas escapes freely. Neither option fully explains what's happening with 3I Atlas. Pure ice bodies are theoretically possible but would be extremely fragile and should show different brightness behaviour. Selective dust retention would require some kind of mechanism to hold particles back while letting gas escape, which doesn't happen naturally in comets. Gas and dust are coupled. You can't have one without the other in the proportions 3I Atlas is showing. And then there's the polarization anomaly. Stay with me on this one because it's technical but important. When light reflects off dust particles or scatters through a gas cloud, it becomes polarized, meaning the light waves a line in certain directions rather than vibrating randomly. The degree and direction of polarization tell you about the size, shape, and composition of the particles doing the scattering. Astronomers have measured polarization from hundreds of comets and asteroids, and there's a well-established range of values. 3i Atlas shows extreme negative polarization that falls outside that range. Not slightly outside, dramatically outside. Negative polarization means the scattered light is polarized in a direction perpendicular to what you'd normally expect, and the degree of polarization is so strong that it suggests the dust particles, or whatever is scattering the light, have properties unlike any cometary or asteroidal dust we've measured before. Maybe the particles are unusually large, maybe they're unusually shaped, maybe they're made of materials with optical properties we don't see in solar system objects. This is the kind of result that makes scientists run their calibrations again, check their instruments, and make sure they're not looking at an artifact. But the observations have been repeated, the polarization anomaly is real, and it's yet another piece of the puzzle that doesn't fit. Now let's return to the metals, because we touched on nickel earlier, but the full picture is even stranger. In addition to nickel, spectroscopy detected cyanide compounds in unusual abundance. Cyanide is not uncommon in comets. It's actually one of the more easily detected molecules because it produces strong emission lines in visible light. But the amount of cyanide relative to water vapor in 3i Atlas is off. It's higher than you'd expect for a normal solar system comet. Cyanide presence tells you about the comet's formation temperature. Cyanide ices are relatively volatile, but require specific conditions to incorporate into a comet during its formation in a protoplanetary disk. An abundance of cyanide suggests this object formed in a region that was cold enough to trap these compounds, but perhaps had a different chemical inventory than our own solar system's outer regions. Combine the cyanide with the nickel, the extreme water outgassing, the low dust production, and the polarization weirdness, and you have an object that doesn't match any single formation scenario scientists can construct. It's as if 3i Atlas is a chimera, a blend of properties that should only appear together under conditions we can't easily model. Again, and I cannot stress this enough, unusual chemistry does not imply artificial origin. The universe is vast. Planetary systems form around stars with wildly different elemental compositions. What seems impossible in our solar system might be perfectly normal around a metal-rich star or in a protoplanetary disk that was seeded by a nearby supernova. The galaxy has been mixing and recycling stellar material for billions of years. Exotic doesn't mean designed. But exotic does mean we're missing something fundamental in our understanding. It means our models, built on observations of solar system objects, and the few interstellar visitors we've studied, are incomplete. And when you're a scientist looking at data that defies all your models, that's when you get excited, because you're on the edge of new knowledge. You're seeing something nobody has fully explained yet. The question is whether the explanation, when it comes, will be a minor adjustment to existing theory, or a complete rethinking of what interstellar objects can be. And as more data poured in from 3i Atlas, that question only grew more urgent. Here's where the story of ʻOumuamua becomes essential, because we've been through this before. We've stood at the edge of not understanding, stared at acceleration data that didn't make sense, and watched as speculation spiraled in every direction. The lesson from ʻOumuamua is critical for how we approach 3i Atlas. It's a lesson about patience, about rigor, and about not letting excitement override careful analysis. When ʻOumuamua was discovered to be accelerating away from the sun without visible outgassing, the scientific community faced a genuine puzzle. The acceleration was small but measurable and could not be explained by gravity alone or by any measurement error. Something was pushing on ʻOumuamua, giving it a tiny boost in velocity as it travelled away from the inner solar system. The question was what? Outgassing was the obvious candidate. Comets accelerate all the time due to the rocket effect of sublimating ice. But ʻOumuamua showed no coma, no tail, no detectable emissions in any wavelength. It looked inert. So if it wasn't outgassing in a way we could see, what was causing the acceleration? This is where the alien hypothesis entered the conversation. If natural outgassing couldn't explain the acceleration, maybe the acceleration was artificial. Maybe ʻOumuamua was a light sail, a thin reflective structure designed to be pushed by starlight, travelling through the galaxy as an interstellar probe. Or maybe it was a derelict spacecraft, tumbling and unpowered but still showing signs of its artificial origin in its motion. These ideas weren't proposed by fringe figures or conspiracy theorists. They were put forward by credentialed scientists, including a Harvard astronomer, and published in peer-reviewed journals. The media, predictably, ran with it. Have we detected alien technology? Headlines exploded across the internet, documentaries were greenlit. The public became fascinated with the possibility that humanity's first interstellar visitor might be our first contact with extraterrestrial intelligence, even if that intelligence had sent only a silent ancient probe. But other scientists pushed back, not because they were close-minded or unwilling to consider exotic explanations, but because the alien hypothesis required extraordinary evidence and there were still natural explanations to exhaust. Teams of researchers went back to the data, ran new simulations and tested alternative models. And eventually, as I mentioned earlier, the hydrogen outgassing hypothesis emerged. The idea was elegant. Cosmic rays constantly bombard objects in interstellar space, breaking down water molecules and other ices into simpler compounds. Molecular hydrogen, H2, could form and become trapped in the ice matrix. When Oumuamua entered the inner solar system and began to warm, this hydrogen would sublimate. But hydrogen is transparent to most wavelengths of light, especially in the diffuse quantities you'd expect from a small object. You wouldn't see a visible coma, you wouldn't detect it with most spectroscopic observations. But it would still exert thrust, still create the rocket effect needed to explain the acceleration. This explanation fit the data. It required no new physics. It relied only on processes we know happen in space. And critically, it made testable predictions about future observations. The scientific consensus shifted. Oumuamua was probably not a spacecraft. It was a comet with an unusual outgassing mechanism. Mystery explained, though not in the most exciting way imaginable. The lesson here is twofold. First, extraordinary claims require extraordinary evidence, and when natural explanations exist that fit the data, those explanations should be preferred until proven inadequate. This is Occam's razor, the principle that simpler explanations are more likely to be correct than complex ones, and it's served science well for centuries. Second, and perhaps more importantly, the universe is weird enough on its own. We don't need to invoke aliens to find mystery and wonder. Oumuamua, even as a natural object, is extraordinary. It's a chunk of another star system, formed in conditions unlike those in our own stellar neighbourhood, travelling for millions of years through the void before happening to pass close enough to our sun for us to detect it. That alone is staggering. The fact that it also shows us exotic physics, processes we don't see in solar system objects, makes it even more valuable. We learn more from a weird comet than we would from a probe that's just passing through without interacting. So when we turn to 3i Atlas, we carry that lesson with us. We approach the anomalies with curiosity but also with discipline. We look for natural explanations first. We test hypotheses rigorously. We don't jump to conclusions. But here's where 3i Atlas presents a different kind of challenge. Oumuamua's acceleration was mysterious because the object appeared inert. There was no visible activity, so the fact that it was accelerating seemed to require something hidden or exotic. With 3i Atlas, the opposite is true. This object is hyperactive, it's visibly outgassing, it's showing all the signs of a comet. By all rights, it should be easier to explain than Oumuamua was, and yet the explanations aren't holding together. The antisolar tail, the chemical composition, the polarization anomaly, the extreme water-to-dust ratio, these aren't hidden mysteries requiring speculation about invisible processes. These are direct observations of behavior that contradicts the standard cometary model. We're watching 3i Atlas do things comets shouldn't do, and we're doing it with some of the most sophisticated instruments ever built. So the question becomes, is 3i Atlas accelerating in non-gravitational ways that add yet another layer of strangeness? And if so, can we explain that acceleration using the same kind of reasoning that worked for Oumuamua, or is something else happening here? Early trajectory analysis suggests 3i Atlas is indeed showing non-gravitational acceleration, though the data is still being refined as observations continue. Given that it's obviously outgassing, this acceleration is less surprising than Oumuamua's. Outgassing creates thrust. That's expected. The issue is whether the magnitude and direction of the acceleration match what we'd predict based on the observed outgassing, or whether there's a mismatch that suggests additional forces at play. If the acceleration matches the outgassing, then at least that part of the puzzle fits. The object is behaving like a comet in that respect. even if everything else about it is bizarre. But if there's a mismatch, if 3i Atlas is accelerating more or less than the visible outgassing would account for, then we're back to square one, back to asking whether there are hidden processes, invisible emissions, or structural properties we're not detecting. The mainstream scientific view right now is that 3i Atlas is a comet from an exotic stellar environment. All its weird properties stem from its unusual formation conditions and composition, not from anything artificial or requiring new physics. It's a strange comet, yes, but a comet nonetheless. The antisolar tail is probably due to asymmetric jets. The chemical composition reflects a protoplanetary disk with different elemental ratios than ours. The polarization anomaly means the dust has unusual properties, not that the dust is artificial. This view is probably correct. It's certainly the most parsimonious. But the fact remains that scientists are still actively studying this object, still running analyses, still trying to build a coherent model that explains all the observations simultaneously. The data keeps coming in, and with each new observation the picture either clarifies or complicates. That's the nature of cutting-edge science. You're working with incomplete information. You're building models that fit most of the data, but not all of it. You're waiting for the one key observation that makes everything click into place, and sometimes you're waiting for the realization that your entire framework was wrong and you need to start over. We're not at the start over point with 3i Atlas, but we're at the scratching our heads point. And that's exactly where the most interesting science happens. There's a particular kind of frustration astronomers experience when an object refuses to look the same twice. You point your telescope at it on Monday, and it's one color, one brightness, one apparent size. You point your telescope at it on Wednesday, and it's different. Not slightly different in ways you'd expect from changing distance or viewing angle. Substantially different, as if the object itself is transforming. 3i Atlas has given astronomers that frustration in abundance. Comets change appearance as they approach and leave the sun. That's normal. They brighten. They develop comas and tails. They fade again. The changes follow predictable curves based on how much ice is sublimating, and how that sublimation responds to increasing or decreasing solar heating. You can model it. You can predict what a comet will look like weeks or months in advance with reasonable accuracy. 3i Atlas didn't follow the curves. Throughout its approach to perihelion, observers noted that the object's colour seemed to shift. Early observations suggested a relatively neutral or slightly reddish hue, consistent with many comets whose surfaces have been darkened and reddened by radiation damage to organic compounds. But as it got closer to the sun and activity increased, reports began coming in of bluish tinges. Blue is not a colour you associate with comets. Asteroids can appear blue if they're made of certain minerals, but comets, especially active ones releasing dust, trend toward red and orange tones. Blue suggests something different. It suggests either gas emissions dominating over dust reflection, or dust with unusual scattering properties, or surface materials being exposed that have different reflective characteristics than the typical organic scovered cometary crust. Each of those possibilities opens its own set of questions. Gas emissions can appear blue if you're seeing scattering from molecules rather than reflection from dust. The blue colour of Earth's sky comes from Rayleigh scattering, where shorter blue wavelengths scatter more efficiently than longer red wavelengths. If 3i Atlas was releasing large quantities of gas with minimal dust, you might see a similar effect in its coma. But we already know it's releasing massive amounts of water vapour, and water vapour doesn't produce a strong blue colour on its own. You'd need other gases, other molecular species contributing to the light we're seeing. Unusual dust scattering properties bring us back to the polarization anomaly. If the dust particles have exotic shapes or compositions, they might scatter light in ways that enhance blue wavelengths over red ones. But this would be highly unusual and would require a very specific set of particle properties. It's not impossible, but it's adding another layer of specificity to an already complex object. Then there's the possibility that we're seeing fresh material being exposed as the surface erodes. Comets develop a dark crust over time as volatile ices sublimate away and leave behind a residue of rocky and organic material. This crust insulates the interior, slowing further sublimation. But if chunks of crust break off, or if jets of gas blast through weak points, you can expose pristine ice beneath, which appears much brighter and bluer than the surrounding surface. Maybe 3i Atlas is shedding its crust in real time, revealing layers beneath that have different colours and compositions. That explanation makes sense for localized bright spots or temporary color changes. But observers reported that the blue coloration appeared in broad regions of the coma, not just isolated jets or specific surface features. It was as if the entire character of the object was shifting, not just its surface. And then there were the jets. Oh, the jets. NASA imagery from around the time of perihelion showed distinct jets erupting from 3I Atlas, streams of gas and dust shooting out from specific points on the nucleus. Jets are common in comets. They form when sunlight heats, localized areas unevenly, creating pressure buildups that release explosively. Jets can persist for hours or days, and they're responsible for much of the fine structure you see in cometary comas and tails. What was unusual about 3I Atlas's jets was their intensity and variability. Some observations showed multiple jets firing simultaneously from different locations. Then the activity would die down, and the object would appear relatively quiet. Then new jets would erupt from completely different areas. The pattern suggested either a very heterogeneous surface with pockets of different volatility, or a nucleus that was tumbling in a complex rotation state that brought different areas into sunlight at different times. Complex rotation is actually a possibility worth considering. If 3I Atlas is tumbling rather than spinning around a single stable axis, its rotation period and orientation would change over time. This would cause dramatic variations in which parts of the surface receive sunlight, leading to unpredictable outbursts as different volatile Riche regions get heated and then cool down again. Tumbling objects are less common than stable rotators, but they're not unheard of, especially among small bodies that might have been jostled by collisions or outgassing torques. But here's the complication. If 3I Atlas is tumbling, that tumbling should show up in its light curve, the graph of how its brightness changes over time. Tumbling objects have characteristic brightness variations as they present different cross-sections to observers. Analyzing the light curve can tell you the rotation period, the shape, and sometimes even the surface properties. Scientists have been studying 3I Atlas's light curve intensely, trying to extract exactly this information. The results have been inconclusive. The light curve shows variations, yes, but they don't fit a simple rotation or tumbling pattern. There are periodic components, but also irregular fluctuations that seem related to outgassing events rather than rotation. It's as if the object is both spinning and erupting, and the two effects are mixing together in ways that make it difficult to separate the geometric signal from the activity signal. Then there's the question of fragmentation. Comets sometimes break apart, especially when they get close to the sun and thermal stresses build up in their interiors. Fragmentation can cause dramatic changes in appearance and activity. A single nucleus becomes multiple pieces, each outgassing independently, and the total brightness can surge as fresh ice is exposed on the broken surfaces. There have been tentative reports that 3I Atlas might be fragmenting, but the evidence is not conclusive. Some images show elongated or multiple bright spots that could be interpreted as a fragmenting nucleus. Other images show a more compact singular appearance. The challenge is that observations are limited by distance and resolution. 3I Atlas is far, away, small and faint. Even with the best telescopes, we're looking at a fuzzy blob with limited detail. Determining whether that blob is one object or several requires very careful analysis of how the light is distributed, and that analysis is ongoing. If 3I Atlas is fragmenting, it would explain some of the erratic behavior. Different fragments could have different compositions, leading to different outgassing patterns. The brightness fluctuations could reflect fragments moving apart or rotating in and out of optimal viewing angles. But fragmentation also raises new questions. Why would this particular interstellar object be prone to fragmentation? Is it structurally weaker than solar system comets? Did something happen during its close solar pass that triggered the breakup? And if it's not fragmenting, if it's staying intact despite all the activity, that's remarkable in its own way. It means the object is strong enough, or its structure is cohesive enough, to withstand the forces trying to tear it apart. That tells you something about what it's made of and how it's held together. All of these observations and questions accumulated during the months of study around perihelion. Scientists collected as much data as possible during this critical window, knowing that once 3I Atlas moved past perihelion and headed back out toward interstellar space, observations would become increasingly difficult. The object would fade as it cooled and got farther from Earth. The window for detailed study would close. That urgency drove an international observing campaign. Telescopes in multiple countries across multiple wavelengths all focused on this one object, trying to capture every possible detail before it slipped away. And what they captured was a portrait of an object in continuous transformation, changing colours, flaring with activity, and refusing to settle into any predictable pattern. It's that refusal to behave consistently that makes 3i Atlas so maddening and so fascinating. Every time observers thought they had a handle on what they were looking at, the object changed. Every time a model seemed to fit the data, new observations would come in that didn't match. It's as if 3i Atlas is deliberately staying just out of reach of full understanding, keeping one more secret for every answer it provides. And as we zoom out from these detailed observations and look at the bigger picture, the question becomes, what does all this strangeness actually mean? Not just for this one object, but for our understanding of what's out there in the galaxy, waiting to be discovered. Let's step back for a moment from the technical details and the specific anomalies and ask a broader question. Why does any of this matter? Why should anyone care whether 3i Atlas has an anti-solar tail or unusual nickel emissions or polarization properties that don't fit models? In the grand scheme of human concerns, why is this small, distant object worth the attention of hundreds of scientists and millions of dollars worth of telescope time? The answer lies in what interstellar objects represent. They're not just curiosities, they're not just oddities that challenge our models, they're messengers from other star systems carrying information we can't get any other way. Think about what we know about the galaxy. We know there are hundreds of billions of stars in the Milky Way. We know that most, probably all of those stars have planetary systems. We've detected thousands of exoplanets, worlds orbiting other stars, and from those detections we've learned that planets are common, diverse, and often very different from the planets in our solar system. We've found hot Jupiters orbiting closer to their stars than Mercury orbits the Sun. We've found super-Earths, planets larger than Earth but smaller than Neptune, a category that doesn't exist in our system. We found worlds orbiting binary stars, planets with multiple suns in their skies. But here's what we can't do yet. We can't study those planets up close. We can't analyse their surfaces, their atmospheres, their compositions in detail. The distances are too vast. Even the nearest stars are light years away, and our fastest spacecraft would take tens of thousands of years to reach them. We can detect exoplanets, we can make educated guesses about their properties based on how they affect their star's light, but we can't touch them. We can't bring samples back. We can't run laboratory analyses on their materials. Interstellar objects are the exception. They come to us. These are pieces of other planetary systems, small bodies that were ejected during the chaotic process of planet formation and sent wandering through the galaxy. When they happen to pass close to our solar system, we can observe them in detail, study their compositions, watch how they behave in real time. They're like ambassadors from distant worlds, bringing us a taste of the chemistry and physics at play around other stars. Every interstellar object we detect expands our sample size. With ʻOumuamua, we learned that some interstellar travellers are rocky and inert, possibly fragments of larger bodies or objects made primarily of refractory materials and hydrogen ice. With 2i Borisov, we learned that interstellar comets can look and behave just like solar system comets, suggesting that comet formation processes are similar across different stellar environments. With 3i Atlas, we're learning that there are objects out there with properties we didn't anticipate, formed under conditions that produce chemical and physical characteristics unlike anything in our own backyard. This diversity matters because it tells us about the range of possibilities in planetary system formation. Our solar system is one data point. It's the only planetary system we can study in exquisite detail, and it's shaped our entire understanding of how planets form and evolve. But it's also just one example. If we base all our theories on this single system, we risk missing entire categories of outcomes that happen under different circumstances. Interstellar objects give us those other data points. They let us test whether our theories, built on solar system observations, actually apply to the rest of the galaxy or whether they need to be revised. When we find an object like 3i Atlas with chemical ratios that don't match our expectations, it tells us that some protoplanetary disks have different starting ingredients. Maybe they formed around stars with different metallicities, stars that have more or fewer heavy elements than our Sun because they formed at different times in galactic history, or in different regions of the galaxy. Maybe 3I Atlas comes from a system where a nearby supernova enriched the protoplanetary disk with unusual elements, leading to comets with high nickel content. Maybe it formed in the debris disk of a stellar collision, where two stars merged and mixed their materials in ways that don't happen in normal star formation. Maybe it's from a system around a binary star where gravitational interactions during planet formation led to different volatile retention and different chemical processing than we see in single-star systems. We don't know. But the fact that 3I Atlas exists, that it has these properties, tells us these exotic scenarios are not just theoretical, they happen. There are places in the galaxy producing objects like this, and if we want to understand the full diversity of planetary systems, if we want to know what kinds of worlds are possible and how common different outcomes are, we need to study as many interstellar visitors as we can. Here's the exciting part. We're about to get a lot more of them. The Vera C. Rubin Observatory, currently under construction in Chile, is designed to survey the entire visible sky every few nights. It will detect faint, fast-moving objects that previous telescopes would have missed. Simulations suggest that once Rubin is operational, we'll discover interstellar objects on a regular basis. Not one every few years, but potentially dozens per year. Maybe more. That flood of data will transform interstellar object studies from a curiosity-driven field focused on individual weird visitors into a statistical science where we can study populations, identify trends, and build comprehensive models. We'll be able to ask questions like, what fraction of interstellar objects are rocky versus icy? How do their compositions cluster? Are there distinct families that come from different types of stellar environments? How often do we see extreme anomalies like 3I Atlas versus more mundane objects like 2I Borisov? Those questions will directly inform our understanding of exoplanetary systems. They'll tell us what to expect when we eventually send missions to other stars or when we develop telescopes powerful enough to study exoplanet surfaces directly. They'll tell us whether Earth-like planets are common, whether the conditions that led to life on Earth are typical or rare, whether the building blocks of life are scattered throughout the galaxy or concentrated in specific environments. This is why 3I Atlas matters. Not because its anti-solar tail is a neat trick, but because every strange property it displays is a clue about the conditions somewhere else in the Milky Way. Not because its chemical composition is personally relevant to us, but because understanding that composition expands the boundaries of what we know is possible, and there's something else. Something more human and harder to quantify, but equally important. Objects like 3I Atlas remind us how much we don't know. They remind us that the universe is larger, stranger, and more diverse than our models capture. In a time when it's easy to feel like science has figured everything out, like all the big questions have been answered, and we're just filling in details, interstellar visitors come along and say, no, you're still just scratching the surface. You still have fundamental mysteries to solve. You still have phenomena that don't fit your theories. That's not a failure of science. That's the lifeblood of science. That's what keeps researchers excited, what drives students to spend years learning physics and astronomy, what justifies the investment in telescopes and spacecraft and computational models. The unknown is what makes science worth doing. 3I Atlas is a gift, even if it's a puzzling one. It's an opportunity to learn, to revise, to expand our understanding, and the fact that it refuses to fit neatly into our existing categories means we're going to learn more from it than we would from an object that behaved exactly as expected. So when scientists say they're baffled by 3I Atlas, that's not a confession of failure. It's a recognition of opportunity. It's the acknowledgement that they're on the edge of something new, and that's exactly where the most exciting discoveries happen. Now, having established why this matters, we need to arrive at some kind of verdict, some synthesis of everything we've discussed. How do we weigh all these anomalies? How do we compare 3I Atlas to ʻOumuamua? And what's the most reasonable conclusion about what we're actually looking at? So here we are, at the end of our investigation, standing at the intersection of data and interpretation, trying to make sense of an object that has refused to make sense from the beginning. Let's lay out what we know with certainty, what we suspect, and what remains genuinely mysterious about 3I Atlas compared to the interstellar visitor that came before it. ʻOumuamua was strange because it didn't act like a comet when it should have. It accelerated without visible outgassing. It looked inert when it should have been active. It had an extreme shape that seemed improbable. Everything about it screamed anomaly because it violated the expectations we had for how a small, icy body should behave when passing through the inner solar system. The strangeness of ʻOumuamua was the strangeness of absence, of things that should have been there but weren't. No tail, no coma, no obvious explanation for its acceleration. That absence created a vacuum that speculation rushed to fill. Maybe it was a hydrogen iceberg. Maybe it was a fragment of a tidally disrupted planet. Maybe it was a light sail. The debate raged because there was so little direct evidence to constrain the possibilities. ʻOumuamua was a Rorschach test, and different scientists saw different things in the limited data available. 3i Atlas is the opposite kind of strange. It's not the strangeness of absence, but the strangeness of excess and contradiction. It acts like a comet, hyperactively so, releasing massive amounts of gas and showing all the hallmarks of cometary activity. But then it does things comets aren't supposed to do. It grows a tail toward the sun. It shows metal emissions in unusual ratios. It displays polarization properties that fall outside known ranges. It changes color in ways that don't follow standard models. It's as if someone took a normal comet and added a dozen asterisks, a dozen footnotes that say, yes, but also this thing that doesn't quite fit. The strangeness of 3i Atlas is the strangeness of presence, of too much happening, too many anomalies stacking up, too many properties clustering outside the comfortable middle of the distribution, and unlike ʻOumuamua, where the lack of data left room for wild speculation, with 3i Atlas we have extensive observations, we have spectroscopy, we have light curves, we have multi-wavelength imaging, we have detailed trajectory analysis. The data is rich, which makes the anomalies harder to dismiss as observational artifacts or misinterpretations. So the question is, does this make 3i Atlas stranger than ʻOumuamua? In terms of raw number of anomalies, yes. 3i Atlas presents more individual puzzles, more specific behaviours that challenge standard models. The anti-solar tail alone would be remarkable. Add the nickel emissions, the polarization, the water-to-dust ratio, the colour changes, and you have a compound mystery that feels more complex than Oumuamua's single big question about acceleration. But in terms of how much these anomalies challenge the fundamental framework, the answer is less clear. Oumuamua forced us to consider whether a non-comet could be accelerating through exotic means, or whether our entire understanding of what qualifies as a comet needed revision. It pushed the boundaries of what natural objects could be, because it seemed to occupy a category we didn't have a name for. It was the visitor that made us question whether we even had the right vocabulary to describe what we were seeing. 3i Atlas, for all its strangeness, still fits within the category of comet. It's just a comet behaving in extreme and unexpected ways. The scientific consensus, the mainstream interpretation that's emerging from the research community, is that 3i Atlas is an interstellar comet from an unusual stellar environment. Its anomalous properties stem from exotic formation conditions, unusual composition, and perhaps structural characteristics we don't yet fully understand, but none of those properties require abandoning the comet framework entirely. The anti-solar tail is probably the result of highly asymmetric outgassing jets that create local flows of material in directions that oppose the solar wind. The metal emissions reflect a protoplanetary disk with different elemental abundances than our solar system, possibly enriched by a nearby supernova or formed around a star with high metallicity. The polarization anomaly means the dust particles have unusual shapes or compositions that scatter light differently, perhaps because they're made of minerals that are rare in solar system comets. The water-to-dust ratio indicates an etheric interior with minimal rocky contamination, possibly because this object formed in the cold outer regions of its home system and never accreted much silicate material. All of these explanations are plausible. None of them require new physics or artificial construction. They require only that we accept the universe produces comets with greater diversity than we've observed in our own solar system, which is not a radical assumption. Of course, interstellar comets are more diverse. They come from hundreds of billions of different planetary systems, each with its own unique conditions and histories. But here's what nags at researchers, what keeps them from closing the book on 3i Atlas and calling it case solved. It's the clustering. Any individual anomaly can be explained away. But when you have 5 or 6 or 10 anomalies in the same object, all pointing in the direction of this is not normal, the cumulative weight becomes harder to dismiss. It starts to feel less like a series of coincidental oddities and more like a coherent signal that we're missing something fundamental. This doesn't mean 3i Atlas is artificial. Let me be absolutely clear about that. There is no credible evidence that this object is a spacecraft, a probe, or any kind of technology. The anomalies are fully consistent with natural processes, just processes happening under conditions that are exotic by solar system standards, but probably commonplace elsewhere in the galaxy. What it does mean is that 3i Atlas is teaching us about regions of parameter space we haven't explored before. It's showing us what happens when you form comets around stars with different chemistries, in disks with different temperatures and pressures, in environments shaped by different nearby events like supernovae or stellar encounters. It's a data point from a part of the universe we can't visit, and it's telling us that part of the universe plays by slightly different rules than the ones we learned here at home. In that sense, 3i Atlas is absolutely stranger than ʻOumuamua, not because it's more likely to be artificial, which it's not, but because it presents a richer, more complex set of challenges to our models. ʻOumuamua was a single deep mystery. 3. The Atlas is a constellation of shallow mysteries, each individually explainable but collectively puzzling. Now let's talk about what comes next, because the story of 3i Atlas is far from over. The object is currently moving away from the Sun, heading back out toward interstellar space, and observations are becoming more difficult as it fades. But there are upcoming opportunities to gather more data. The European Space Agency's Jupiter Icy Moons Explorer JUICE has instruments that could potentially observe 3i Atlas from a different vantage point. NASA's Juno spacecraft, currently in orbit around Jupiter, might be able to contribute observations depending on viewing geometry and timing. More importantly, scientists are still analysing the data that's already been collected. There are terabytes of images, spectra, and measurements sitting on hard drives and servers around the world, waiting to be fully processed and interpreted. Some of the most important findings about 3i Atlas might not come from new observations, but from deeper analysis of what's already been captured. Pattern recognition algorithms will search for periodicities in the light curves. Chemical models will try to reproduce the observed emission spectra. Dynamical simulations will test whether the antisolar tail can be explained by plausible jet configurations. This process takes time, it takes collaboration, it takes researchers from different disciplines bringing their expertise to bear on the same problem, and it takes patience. Because unlike fast-breaking news stories, scientific understanding builds slowly through peer review, replication, and consensus formation. But even as that process unfolds, we can draw some provisional conclusions. 3. Atlas refuses to follow the rules, not because it's breaking the laws of physics, but because the rules we wrote were based on insufficient data. Our understanding of what interstellar objects can be was shaped by the limited sample available to us. ʻOumuamua, 2i Borisov, and now 3i Atlas. 3 objects is not a population, it's barely even a sample, it's 3 anecdotes. If you tried to describe the diversity of animals on Earth based on studying 3 species, you'd miss everything important. You might happen to pick a fish, a bird, and a mammal, and think you understood the range of life, but you'd have no idea about insects, reptiles, amphibians, or any of the strange and wonderful variations within those categories. You'd have a framework, but it would be cartoonishly incomplete. That's where we are with interstellar objects. We have a rough framework. We know they can be rocky, like ʻOumuamua, or icy, like 2i Borisov. We know they can be active or inert, fast-moving or slow, large or small. But we don't know the full range of possibilities. We don't know how common extreme objects like 3i Atlas are versus more mundane visitors. We don't know whether the anomalies we're seeing are representative of broad categories, or whether every interstellar object is weird in its own unique way. The Virasi-Rubin Observatory will help answer those questions. When it comes online and starts detecting interstellar objects regularly, we'll be able to do real statistics. We'll be able to say, X% of interstellar visitors show this property, Y% show that property, and Z% are outliers that don't fit any simple category. We'll build a taxonomy, a classification system that captures the real diversity of what's out there. Until then, we're in the era of surprises. Every new interstellar visitor has the potential to overturn our expectations because our expectations are based on such limited data. 3i Atlas surprised us. The next visitor might surprise us even more. Or it might be perfectly ordinary, fitting comfortably into the models we're developing, and in some ways that would be just as valuable, because it would confirm that the weird objects are genuinely outliers, not the new normal. Here's my take, having walked you through all the evidence and all the mysteries. 3. ʻAtlas is stranger than ʻOumuamua in the sense that it presents more anomalies and challenges more aspects of our standard comet model, but it's less philosophically strange because it doesn't force us to question fundamental categories the way ʻOumuamua did. It's a comet, just an exotic one from an environment we've never sampled before. The real story isn't about ranking which visitor is weirder. The real story is that the universe is revealing its diversity to us, one interstellar traveller at a time, and we're learning that what we thought were universal rules are actually local trends. Comets in our solar system behave a certain way because they formed here, from the specific mix of materials that happened to be in our protoplanetary disk when the planets were forming. Comets from other systems behave differently because they formed elsewhere, from different materials under different conditions. That's not mysterious. That's just chemistry and physics playing out across a vast galaxy with infinite local variations. What's mysterious is the specifics, the details of how those variations manifest. And that's what makes objects like 3i so valuable. They fill in those details, they show us specific examples of outcomes we hadn't predicted, they expand the possibility space. So if you came to this video wondering whether 3i is weirder than ʻOumuamua, the answer is yes, in terms of sheer number of strange properties. But both objects are part of the same larger story. The story of humanity beginning to study the galaxy, not just from a distance, but through direct contact with its smaller representatives. Every interstellar visitor is a chapter in that story. ʻOumuamua was the opening chapter, the one that announced this new field of research. 3i is the chapter that complicates the plot, that introduces new characters and new questions. The next chapter hasn't been written yet. It's out there somewhere, tumbling through the space between stars, on a trajectory that might bring it close enough to our sun for us to detect it. Maybe it will answer the questions 3i raised. Maybe it will raise new ones. Maybe it will be so ordinary that it fades into the background as we accumulate more data. Or maybe it will be stranger still, the object that finally forces us to completely rethink what we thought we knew. That uncertainty is part of the excitement. That's what keeps researchers scanning the skies, running detection algorithms and building better telescopes. Because somewhere in the data stream, hidden among millions of ordinary stars and asteroids and cosmic noise, is the next visitor, and we have no idea what it's going to show us. If this deep dive into the mysteries of 3i changed how you think about what's out there, if it gave you a sense of just how much we're learning from these cosmic messengers, then consider subscribing. Because when the next interstellar visitor arrives, and it will arrive, we'll be here to investigate it together. We'll ask the same hard questions. We'll look at the same confusing data, and we'll try to make sense of it, not by jumping to dramatic conclusions, but by following the evidence wherever it leads. Drop a comment and tell me which anomaly you found most intriguing. Is it the anti-solar tail that defies physics? The nickel emissions that suggest exotic chemistry? The polarization mystery that hints at dust unlike anything we've seen? Or is it something else, some detail in this story that caught your attention and made you wonder? I want to know what resonates with you, what questions you're left with, because those questions are what drive science forward. 3. ʻAtlas is still out there, moving away from us, carrying its secrets back into the darkness between stars. We had a brief window to study it, and we took full advantage, gathering more data than we could have dreamed of a decade ago. Now the work shifts from observation to interpretation, from collecting data to understanding what it means. That work will continue for years. Papers will be published. Theories will be proposed and tested. Debates will happen at conferences and in journal pages. And through it all, the object itself will keep moving, indifferent to our efforts to explain it, following the gravitational choreography set in motion millions of years ago when it was ejected from its home system. It doesn't care whether we call it strange or ordinary, whether we understand its anti-solar tail or its chemical composition. It's just doing what interstellar objects do, travelling through the galaxy, occasionally passing, close enough to a star to remind the inhabitants of that star that they're not alone, that the universe is vast and filled with wonders, and that there's always something new to learn if you're willing to look up and ask the right questions. That's the real lesson of 3i. Not that it's weirder than ʻOumuamua, though it is. Not that it defies explanation, though it challenges our models. The real lesson is that the universe is bigger and stranger, and more diverse than any framework we build can fully capture, and that's exactly how it should be, because a universe that fit neatly into our models would be a smaller, less interesting place. A universe that keeps surprising us, that keeps presenting new mysteries and new challenges, is a universe worth exploring. 3i Atlas gave us that reminder. It showed up, refused to follow the script, and left us scratching our heads and smiling at the audacity of nature. And now it's someone else's turn. The next visitor is out there. We just have to wait for it to arrive and see what new rules it decides to break. Until then, keep looking up, keep asking questions, and keep that sense of wonder alive, because it's the fuel that drives all discovery. Thanks for staying with me through this investigation. Now go forward with eyes a little wider, knowing that the next cosmic mystery could be spotted any day, and when it is, we'll be ready to dive in and figure it out together.